Hello everyone, welcome back. I'm your friend in Saxo. Today we are going to continue to learn the Algebra 1. This is a fresh new journey for us because we are finally getting into the core parts. Let's have a look at the algebra itself. The history of algebra. I didn't notice that I probably have seen all those courses before, but it's fine. Let's do it again.
What I want to do in this video is think about the origins of algebra. The origins of algebra. And the word, especially in association with the ideas that algebra now represents, comes from this book, or actually this is a page of the book right over there. The English translation for the title of this book is The Compendious Book on Calculation by Completion and Balancing. And it was written by a Persian mathematician who lived in Baghdad in I believe it was in the 8th or 9th century. I believe it was actually 820 AD when he wrote this book, AD. And algebra is the Arabic word that here's the title that he gave to it, which is the Arabic title. Algebra means restoration or completion. Restoration or completion. And he associated it in his book with a very specific operation, really taking something from one side of an equation to another side of an equation. But we can actually see it right over here. And I don't know Arabic, but I actually do know some languages that seems to have borrowed a little bit from Arabic, or maybe it went the other way around. But this says Al-Kitab, and I know just enough Urdu and Hindi to understand a good Indian movie. But Al-Kitab means book. So this part is book. Al-Muqtazar, I think that means compendious, because I don't know the word for compendious, and that seems like that. Fi Hisab means calculation in Hindi or Urdu, so this is calculation. Algebra, this is the root. This is the famous algebra. This is where it shows up. So this is for completion. You could view that as completion. And then wa al-muqabla, and that means essentially balancing, completion and balancing. So if we wanted to translate, and I know this isn't a video on translating Arabic, but the book, I guess this is saying compendious on calculation by completion and balancing is the rough translation right over there. But that is the source of the word algebra. And this is a very, very, very important book, not just because it was the first use of the word algebra, but many people view this book as the first time that algebra took took on many of its modern ideas of balancing an equation, the abstract problem itself, not trying to do one-off problems here or there. But Al-Khwarizmi was not the first person, and just to get an idea of where all of this is happening. So he was hanging out in Baghdad, and this part of the world shows up a lot in the history of algebra, but he was hanging out right there in around the 8th or 9th century. So let me draw a little timeline here just so we can appreciate everything. So that is timeline. And then whether or not you are religious, most of our modern dates are dependent on the birth of Jesus. So I will put, so that is right there. We'll put a cross over there to signify that. When we want to be non-religious, we say Common Era, before the Common Era. When we want to be religious, we say AD, which means in the year of our Lord. I don't know the Latin. Anno Domini, I believe, year of our Lord. And then when we want to, and in the religious context, instead of saying before Common Era, we say before Christ, BC. But either way. So this is 1000 in the Common Era. This is 2000 in the Common Era. And
to be honest, I don't know why this is important to introduce the origins of algebra. For now, as far as we know, it's just let's say theory behind the numbers, and that's all. And introduction to variables, we have already known what is variable, and we have also known what is expression, so we don't have to look at that. Intro to combining like terms, what is that?
Let's say that I've got two Chuck Norrises, or maybe it's Chuck Norri, and to that I am going to add another 3 Chuck Norrises. I'm going to add another 3 Chuck Norrises, and this might seem a little bit obvious, but how many Chuck Norrises do I now have? Well, 2 Chuck Norrises, we can represent this as literally a Chuck Norris plus a Chuck Norris. Let me do that, a Chuck Norris plus another Chuck Norris. 2 Chuck Norrises, you could also view this as 2 times Chuck Norris, and this is just another way of representing it. And 3 Chuck Norrises, you could view that as a Chuck Norris plus a Chuck Norris Norris plus another Chuck Norris. And so we would have a grand total, and this might be very simple for you, but you would have a grand total of 1, 2, 3, 4, 5 Chuck Norrises. So this would be equal to 5 Chuck Norrises. Now let's get a little bit more abstract here. Chuck Norris is a very tangible thing. So let's go to a little bit more of traditional algebraic notation. If I have two x's, and remember, 2x, this is what you could do this as 2x's or 2 times x, and to that I were to add 3x's, and to that I would add 3x's. How many x's do I have? Well, once again, 2x's, that's 2 times x. You could view that as an x plus an x. We don't know what the value of x is, but whatever that value is, we can add it to itself. And then 3x's are going to be that value. Let me do that in that same green color. 3x's are going to be that value plus whatever that value is. And so how many x's do I now have? Well, I'm going to have 1, 2, 3, 4, 5 x's. So 2x plus 3x is equal to 5x. And if you think about it, all we really did, and hopefully you conceptually get it, is we just added the two numbers that were multiplying the x. And these numbers, the 2 or the 3, they're called coefficients. Very fancy word, but it's just this constant number, this regular number that's multiplied by the variable. You just added the 2 and the 3 to get your 5x. Now let's think about this a little bit more. Let's go back to this original expression, the 2 Chuck Norrises plus 3 Chuck Norrises. Let's say to that we were to add, some type of a, let's say we were to add 7 plums over here. So this is my drawing of a plum. So we have 7 plums plus 2 Chuck Norrises plus 3 Chuck Norrises. And let's say that I add another 2 plums. I add another 2 plums here. So what would this whole thing be? Well, I wouldn't add the 7 to the 2 to the 3 plus the 2. We're adding different things here. You have 2 Chuck Norrises and 3 Chuck Norrises. So they're still going to simplify to 5 Chuck Norrises. And then we would separately think about the plums. We have 7 plums and we're adding another 2 plums. We're going to have 9 plums plus 9 plums. So this simplifies to 5 Chuck Norrises and 9 plums. Similarly, over here, if I had, instead of just 2x plus 3x, if I had 7y plus 2x plus 3x plus 2y, what do I now have? Well, I can't add the x's and the y's. They could very well represent a different number. So all I can do is really add the x's, and then I get the 5x, and then I'd separately add the y. If I have 7 y's, and to that I add 2 y's, I'm going to have 9 y's. If I have 7 of something and I add 2 of something, I now have 9 of that something. So I'm going to have 9 y's. So you add that, do that in a different color. You add this and this, you get that. You add the x's, you get that right over there. So hopefully that makes a little sense. Actually, I'll throw out one more idea. So given this, what would happen if I were to have 2x plus 1 plus 7x plus 5? Well, once again, you might be tempted to add the 2 plus the 1, but they're adding different things. These are 2 x's. This is just the number 1. So you really just have to add the x's together. So you're going to say, well, I got 2 x's, and I'm going to add 7 x's to that. Well, that means I now have 9 x's. And then separately, you would say, well, I've got just the abstract number 1, and then I got another 5. 1 plus 5 is going to be equal to 6.
Alright. Combinations. Okay.
I've gotten feedback that all of the Chuck Norris imagery in the last video might have been a little bit too overwhelming. So for this video, I've included something a little bit more soothing. So let's try to simplify some more expressions, and we'll see we're just applying ideas that we already knew about. So let's say I want to simplify the expression 2 times 3x plus 5. Well, this literally means 2 3x plus 5s. So this is the exact same thing as, so this is 1 3x plus 5, and then to that, I'm going to add another 3x plus 5. This is literally what 2 times 3x plus 5 means. Well, this is the same thing as, if we just look at it right over here, we have now 2 3x's, so we could write it as 2 times 3x, plus we have 2 5s, so plus 2 times 5. But you might say, hey Sal, isn't this just the distributive property that I know from arithmetic? I've essentially just distributed the 2 times 3x, plus 2 times 5, and I would tell you, yes, it is. And the whole reason why I'm doing this is just to show you that it is exactly what you already know. But with that out of the way, let's continue to simplify it. So when you multiply the 2 times the 3x, you get 6x. You multiply the 2 times the 5, you get 10. So this simplified to 6x plus 10. Now let's try something that's a little bit more involved, but once again, really just things that you already know. So let's say that I had 7 times, 3y minus 5 minus 2 times 10 plus, plus 10 plus 4y. Let's see if we can simplify this. Well, let's work on the left-hand side of the expression, the 7 times 3y minus 5. We just have to distribute the 7. So this is going to be 7 times 3y, which is going to give us 21y. Or if I had 3y's 7 times, it's going to be 21y's. Either way you want to think about it. And then I have 7 times, we're going to be careful with the sign. This is 7 times negative 5. 7 times negative 5 is negative 35. So we've simplified this part of it. Let's simplify the right-hand side. So you might be tempted to say, oh, 2 times 10 and 2 times 4y, and then subtract them. And if you do that right and you distribute the subtraction, it would work out. But I like to think of this as negative 2. As negative 2. And we're going to distribute the negative 2 times 10. And then we're going to distribute the negative, or times 10, and then negative 2 times 4y. So negative 2 times 10, negative 2 times the 10 is negative 20. So it's minus 20 right over here. And then negative 2 times 4y, negative 2 times 4 is negative 8. So it's going to be negative 8y. So write a minus 8y right over here. And are we done simplifying? Well, no, there's a little bit more that we can do. We can't add the 21y to the negative 35 or the negative 20 because these are adding different things or subtracting different things. But we do have two things that are multiplying y. We have the, let me do them all in this green color. You have 21y's right over here. And then from that, we are subtracting, or we can view it as, from that, we are subtracting 8y's. So 21 of something, if I have 21 of something and I take 8 of them away, I'm left with 13 of that something. So those are going to simplify to 13y's. And then I have negative 35, this is in a new color. And then I have negative 35 minus 20. And so that's just going to simplify to negative 55. Negative 55. So this whole thing simplified using a little bit of the distributive property and combining.
Okay, if you think about this, you will generally notice that the 21y and the negative 8y, they are just the same type of variable. You could think it like that. So you could do the same operation on two of them. And if you think about the negative 35 and the negative 20, they are just the same type of numbers. So you could combine them together to get this one. Then you add them both together, you get the final answer. Introduction to equivalent expressions.
Which expressions are equivalent to x plus 2y plus x plus 2? Select all that apply. All right, let's see if I can manipulate this thing a little bit. Let me just rewrite it. So I have x plus 2y plus x plus 2. So the first thing that jumps out at me before I even look at these choices, here I have an x over here, I have an x over there. Well, if I have one x and then I can add it to another x, that would be 2x. So I could rewrite this. Let me do this in a different color. I could rewrite this x and this x. If I add them together, that's going to be 2x. So this is, let me, I don't want to skip any steps. So that's x plus 2y. Now I'm just switching the order, plus 2. And then these two x's right over here, I can just rewrite that as 2x. So 2x plus 2y plus 2y plus 2. Now let's see, out of all of my choices, so this one, this is 2x plus 4y plus 4. So that's not right. I have 2x plus 2y plus 2. So I can rule this one out. Now this one's interesting. It looks like they have factored out a 2. Let's see, if we factor out a 2 here, what happens? So we do see that 2 is a factor of that term, it's a factor of that term, and it's a factor of that term. Let's see if we can factor it out. This is going to be 2 times x. I'll do the x in that same magenta color. 2 times x plus, you have just a y left when you factor out the 2. And then if you factor out a 2 here, you're just going to have a 1 left. So 2 times x plus y plus 1, which is exactly what they have over here. And since I was able to find a choice, I will not pick none of the above.
As far as I say, or as far as I know, I do not think the division by zero would be a successful operation.
Comedian Stephen Wright, and I guess we should also credit him maybe with being a bit of a philosopher, once commented that black holes are where God divided by zero. And I won't get into the physics of it, and obviously the metaphor breaks down in certain ways, but it is strangely appropriate because black holes are where our current understanding of physics seem to break down, and dividing by zero, as simple of an idea as that seems to be, is where our mathematics also breaks down. This is undefined. And sometimes when you see undefined when you're in math class, it seems like a very strange thing. It seems like a very bizarre idea, but it really means exactly what the word means. Mathematicians have never said what it must mean to divide by zero. What is that value? And the reason they haven't done it is because they couldn't come up with a good answer. There's no good answer here, no good definition. And because of that, any non-zero number divided by zero is just left undefined. 7 divided by 0, 8 divided divided by 0, -1 divided by 0. We say all of these things are just undefined. Now you might say, hey, well, if we can just define it, let's at least try to come up with a definition of what it means to take a non-zero number divided by 0. So let's do that right now. Now we could just take the simplest of all non-zero numbers. We'll just do it with 1, but we could have done this with any non-zero number. Let's take the example of 1, and since we don't know what it means, or we're trying to figure out what it means to divide by 0, let's just try out really small positive numbers. Let's divide by really small positive numbers and see what happens as we get close to 0. So let's divide by 0.1. Well, this will get us to 10. If we divide 1 by 0.01, that gets us to 100. Let me go really close to 0. If I divide 1 by 0.0000001, this gets us, so this is not a 10th, 100th, 1000th, 10,000, 100,000. This is a million. 1 divided by a million, that's going to give us 1 million. So we see a pattern here. As we divide 1 by smaller and smaller positive numbers, we get a larger and larger value. So based on just this, you might say, hey, well, I've got somewhat of a definition for 1 divided by 0. Maybe we can say that 1 divided by 0 is positive infinity. As we put smaller and smaller positive numbers here, we get super large numbers right over here. But then your friend might say, well, that worked when we divided by positive numbers close to 0, but what happens when we divide by negative numbers close to 0? So let's try those out. Well, 1 divided by 0.1, or I should say negative 0.1, that's going to be -10. 1 divided by negative 0.01, that's going to be -100. And if we go all the way to 1 divided by negative 0.000001, yep, I drew the same number of zeros, that gets us to -1 million. And so when we keep dividing 1 by negative numbers that are closer and closer to 0, we get a very different answer. We actually start approaching negative infinity. So over here we said maybe it would be positive infinity, but you can make an equally strong argument that it could be a very different number. Negative infinity is going the exact opposite direction. So you can make an equally strong argument that it should be negative infinity. And this is why mathematician says, well, there's just no good answer here, especially one that's consistent with the rest of mathematics. They could have just said it's equal to, 42 or something like that, but that would make no sense. Neither one of these values, and it wouldn't be consistent with everything else we know. So they just left the whole thing undefined.
Okay, now I know why people said that a number divided by 0 is undefined. Because for sometimes it's equal to positive infinity, and in another time it's equal to negative infinity. But this cannot be the same thing. So in the end, people just say, well, then we say that a number divided by 0 is undefined.
So once again, let's think of, well, maybe the best way of finding out what x divided by 0 should grow. And I'm not willing to give up the idea, either of these ideas. I'm not willing to give up the idea that if I'm defining what it means to divide by 0, or if I'm defining what it means to divide by anything, that if I then multiply by that something, that I should get my original number. And I'm not willing to give up to this magenta 0. This should simplify to this, right? Assumptions up here. This could be predictions. 0 divided by 0. It could be anything. You can't determine it. And so that's why, as you get to higher level of math, and you'll often hear this when you take a calculus course, we say that 0 divided by 0 is indeterminate.
Oh, when I hear this word indeterminate, I think this course is very important for you to understand, because when you get into a higher level, you will have to deal with this kind of idea, 0 divided by 0 pattern.
So once again, let's think of yourself as some type of ancient philosopher / mathematician who's trying to extend mathematics as much as possible and trying to make sure that you're not being lazy and leaving things undefined when you might be able to define them. But whenever you start extending mathematics, especially in the realm of multiplication and division, there are a few things that you hold dear to. You feel that if you define some type of division operation, that it needs to be undone by multiplication. This is close to your heart. So you would like to assume that any type of division operation, if you start with some number, and if you were to divide with a number over which that division by that number is defined, so if I were to divide by some number and then multiply by that same number, that this should get me this original number right over here. This should give me x right right over here. And this happens with just when we just multiply and divide with regular numbers. If I get 3 divided by 2 times 2, that's going to get me 3. If I say 10 divided by 5 times 5, that's going to get me 10. The other thing that I want to assume, this is very close to my heart, I feel that any type of definitions I make have to be consistent with the idea x times 0, and I'll use a dot for times here. X times 0 has to be 0 for any x. So these are close to my heart. If I'm going to extend mathematics, these two things are things that cannot be contradicted, cannot be untrue. Now, with that out of the way, you want to start exploring the divide by 0 question. So the first thing that you say is, well, let me just try to define it. So let's assume that I have, let's make a further assumption that x is some non-zero number. X is some non-zero number. And let's just say, well, maybe the best way of finding out what x divided by 0 should be, how I should define it, is just assume that it's defined and then come up with any results that I might, or maybe I'll even be able to solve for it. So let's say that x divided by 0 is equal to, let's say that it is equal to y. Well, I'll use a different number just to not get you confused with this up here. Let's say it's equal to, let's say that it is equal to k. Well, if this is true, and if we're defining what it means to divide by 0, then we're assuming that if we multiply by 0, we need to get our original number right over here. This is something that we are not willing to contradict. So let's see what happens. X divided by 0 is equal to k. On the left-hand side, I'm going to divide by 0 and then multiply by 0. Well, if two things are equal and if I do something to one thing, in order for them to stay equal, I have to do it to the other thing. This has to be equal to that. I have to multiply both the left and the right-hand sides by 0. Well, by this assumption that I'm never willing to give up, this left-hand side right over here must be equal to x. This must be equal to x. And by this assumption right over here that I'm not willing to give up, this right-hand side right over here must be equal to, 0. But I just hit a contradiction. I assume that x does not equal to 0, and now I'm being forced to say that x equals 0. And I'm not willing to give up the idea, either of these ideas. I'm not willing to give up the idea that if I'm defining what it means to divide by 0, or if I'm defining what it means to divide by anything, that if I then multiply by that something, that I should get my original number. And I'm not willing to give up the idea that anything times 0 is 0. So out of all of these things, the only thing that I can give up is this right over here. And I'll say, well, I guess k will have to stay undefined. This whole contradiction happened because I attempted to define what x divided by 0 is. Now, with that out of the way, you're like, well, okay, this was the situation when x does not equal 0. But what about when x does equal 0? So let's think about that for a little bit. And once again, I will try to define it. So I will assume that 0 divided by 0 is equal to some number. Well, once again, let's say it's equal to k again. And so once again, we're going to try to do the same logic. So I'm going to rewrite it again. 0 divided by 0 is equal to k. And actually, let me color code the zeros. So that's a magenta 0. This is a blue 0 right over here. And once again, I'm not willing to give up the idea that if I start with a number, x, I divide it by something over which division is defined, and then I multiply by that something, that I should get my original x again. Can't give this up. Otherwise, it doesn't seem like a good definition for division. So what I'm going to do is I'm going to multiply the left-hand side times 0, and by this property that I'm not willing to give up, the left-hand side should simplify to this magenta 0. This should simplify to this right over here. But once again, anything I do to one side of an equation, in order for the equation to hold true, I need to do the other side of the equation. If these two were equal beforehand, any operation I do to this, in order for it to still be equal, I need to do to that. So let me multiply the right-hand side. By 0. So on the left, I get 0. I just get this magenta 0. And on the right, I get, I could just write a 0 here, but I won't simplify it. I get k times 0. Well, this I see right over here. This actually is not a contradiction. This is actually true for any k. This is actually one of my core assumptions that I made in my mathematics that I'm not willing to give up. So this is true, and let me write it bold. This is true for any. This is true for any k. It's not a contradiction, but the problem here is I wanted to come up with the k. I wanted to almost solve for k. It would have been nice if this turned out to be 0, or if this turned out to be 1, or this turned out to be -1. But now I'm seeing that given the assumptions up here, this could be any. This could be absolutely any k. I cannot determine what k this should be. This could be 100,000, this could be 75, it could be anything. True for any k. I cannot determine cannot determine what k this should be. And that's why when you get a little bit more nuance in early math, people will say, well, 0 divided by 0, well, we don't know what that's going to be. There's no consistent answer there. So we're just going to call it undefined. There's no good answer that seems to be better than any other answer. But now we see a little bit of nuance here. 1 divided by 0, you just couldn't define it. It led to direct contradictions. 0 divided by 0, it could be anything. You can't determine it. And so that's why, as you get to higher level of math, and you'll often hear this when you take a calculus course, we say that 0 divided by 0 is indeterminate. Indeterminate.
Okay, indeterminate. Then I guess this is the end for the algebra foundations we got it in row. That's probably I could say that's today's course, but okay, let it be here. So the learning is a general process. It's a constant process. It's not something that you can get to it with 1 hour or overnight. That's not possible. But the only possible thing that we could know is that if you persist enough, if you keep doing this thing, you could be really good at it. That's something without any doubt. Okay, that's today's learning, and inside of this video we have learned about the algebra foundations, and I hope you enjoy this. I will see you in the next video. Bye.